Good day, Bayaw. Today, we will be solving another problem from the book of Thermodynamics by Singal, Chapter 7, the refrigeration cycle. A heat pump that operates on the ideal vapor compression cycle with refrigerant 134A is used to heat water from 15 degrees Celsius to 45 degrees Celsius at a rate of 0.12 kg per second. The condenser and evaporator pressures are 1.4 megapascal and 0.32 megapascal, respectively. Determine the power input to the heat pump. First, we will be identifying our given. So we have here the temperature at state 1 that is equal to 15 degrees Celsius. Temperature at state 2, 45 degrees Celsius. Mass per unit time that is equal to 0.12 kg per second. Pressure at state 1 that is 0.32 megapascal, pressure at state 2 1.4 megapascal, and this the power input to the heat pump. So first, we will be identifying the specific enthalpy of this state 1, that is the H1 that is equal to Hg, or the specific enthalpy of the vapor at 32 or 320 kilopascal, that is equal to 251.88 kilojoules per kilogram. So here you will be find that value here in the table A-12 at saturated refrigerant 134A pressure table. So that the 320 kilopascal. Next is the specific entropy at state 1 that is also equal to the specific entropy of the vapor at 320 kilopascal. Here, that is the equal to 0.93006 kilojoules per kilogram Kelvin. Next, to find the specific enthalpy at state 2, we will be using the value of our pressure at state 2 that is equal to 1.4 megapascal. So here at the table A-13 at superheated refrigerant 134A, you will be using this pressure here that is 1.4 megapascal. So since we don't have that exact value of our specific entropy, so here we will be using this S sub 1, the specific entropy at state 1, the 0.93006. So you can find it directly, this value here. So we will be using the linear interpolation of this equation here, the specific entropy top minus the specific entropy bottom over the specific entropy at state 1 minus the specific entropy bottom is equal to the specific enthalpy of the top minus the specific enthalpy of the bottom over the specific enthalpy at state 2 minus the specific enthalpy of the bottom. So to have this final equation here, we rearrange it to have our value of the specific enthalpy at state 2. So we have this equation, another equation here, the specific S1 minus S bottom times the H top minus H bottom divided by the S top minus S bottom plus the H bottom. So we will be plugging in the values. We have the 0.93006 minus 0.9105 kilojoules per kilogram Kelvin times 285.47 minus 276.12 kilojoules per kilogram divided by 0.9389 minus 0.9105 kilojoules per kilogram Kelvin plus 276.12 kilojoules per kilogram. So we have this specific enthalpy at state 2 that is equal to 282.56 kilojoules per kilogram. Next, at state 3, we have this pressure at state 3 that is also equal to the pressure at state 2, that is 1.4 megapascal. So the specific enthalpy at state 3 is also equal to the specific enthalpy of the liquid at 1.4 megapascal. So that is equal to 127.22 kilojoules per kilogram. So you can find it here in our table at table A-12 in saturated refrigerant 134A pressure table. That 1.4 megapascal is also equal to 1,400 kilopascal. Since we are in state 3 to 4, this state here is adiabatic, so it is in a throttling process. So that means that the enthalpy in this process is constant. We have this H3 that is also equal to our specific enthalpy at state 4, that is 127.22 kilojoules per kilogram. Next, we have here another equation that is the heat of our heat pump is equal to the mass per unit time times the constant pressure of the specific heat times the change in temperature, that is the temperature at state 2 minus the temperature at state 1 of our water. So we plug in our values. We have the 0.12 kilogram per second times 4.18 kilojoules per kilogram degrees Celsius times 45 minus 15 degrees Celsius. So we have this, the heat of our heat pump, that is equal to 15.05 kilowatts. So to find the mass per unit time of our refrigerant, we have this equation that is equal to the heat of our heat pump divided by the specific heat of our heat pump. So that is also equal to the heat of our heat pump divided by the specific enthalpy at state 2 minus the specific enthalpy at state 3. So we'll be plugging in the values. We have this 15.05 kilowatts divided by 282.54 minus 127.22 kilojoules per kilogram. And we have here our mass per unit time of the refrigerant that is equal to 0.09688 kilogram per second. So lastly, to solve the power input of our heat pump, we have this work input is equal to the mass per unit time of our refrigerant times the specific enthalpy at state 1 minus the specific enthalpy at state 2. So we plug in the values. We have this 0.09688 kilogram per second times 282.56 minus 251.88 kilojoules per kilogram, and we have this, the work input of the heat pump, that is equal to 297 kilowatts. And that is our final answer.